In today's video, we'll learn about standing waves. Standing waves can be achieved by stretching a string and connecting one end of the string to a stationary clamp and connecting the other end to a vibrating object. For example, like shaking your hand holding the string up and down at a steady rate. If we were able to shake the string at the right frequency, the wave would appear to stand still. When the wave appears to stand still, we can observe nodes and antinodes within the standing wave. A node occurs when two traveling waves have the same magnitude of displacement but opposite signs. Therefore, the net displacement is zero at that point and there is no motion in the string at the node. While midway between two nodes, the antinode is located. Here, the string vibrates with the largest amplitude. So if we were to take a quick look to our figure to the right, we see we have a standing wave which would appear as 3 loops. And at the end of each loop, we'd observe a node, and between two nodes at its highest amplitude, we would observe the antinode. The lowest frequency of vibration to create a standing wave is called the fundamental frequency. And at this frequency, the vibrating string only has nodes at the end where the string is attached. This is also known as the first harmonic. We can calculate the frequency of the first harmonic, which is equal to 1 over 2 times the length of our string multiplied by the velocity of our string, or the square root of the tension in our string divided by mu, which is the mass per unit length of the string. And in our figure to the right, our first string we see is an example of the fundamental frequency, or the first harmonic, where the node is located only at the ends where the string is attached. We can also calculate the frequency of a string at a higher harmonic with the equation that n, which is the number of the harmonic, divided by 2 times the length of the string, multiplied by the square root of the tension of the string divided by the mass per unit length of the string, which we see is just the velocity of the wave. So by looking at our figure to the right, we see that the wavelength of a string can be calculated by taking 2 times the length divided by our number of harmonics will give us the wavelength of our string, while the frequency of the string can be calculated by taking the number of the harmonics multiplied by the wave speed, which is also the same as the square root of our force divided by mu, divided by 2 times the length of the string. We can also see that standing waves also occur in air columns. And this is a relationship between the incident wave and the reflected wave. Depends on where the reflected end of the tube is open or closed. So if one end is closed, a node must exist at that end because the movement of air is restricted. If that end is open, the elements of air have complete freedom of motion and an antinode exists. So if we look at our figure at the right, we see we have an open end pipe as well as an open end pipe with a closed end pipe. At our open end pipe, we can observe antinodes, while at the closed end of the pipe, we observe a node. So standing waves in an open end pipe is where the pipe is open at both ends and all harmonics can be present. So we see that our equation to solve for the frequency of a standing wave in an open pipe is no different than the equation we learned in our last slide, which stated that our frequency is equal to our wave speed divided by our wavelength, or it's equal to the number of our harmonics multiplied by our wave speed divided by 2 times the length. While standing waves in a closed-end pipe is when the pipe is open at one end but closed at the other end. Here, only odd harmonics are present, such as our first harmonic, our third harmonic, and our fifth harmonic. And this can be seen to the far right in our figure, where one end is open and one end is closed. In order to solve for a frequency in a closed pipe, we see that our equation differs. Here, n is still our number of harmonics, which can only be an odd harmonic, multiplied by the wave speed divided by 4 times the length. In our first example, it states that a stretched string fixed at each end has a mass of 40 grams and a length of 8 meters. The tension in the string is 49 newtons, and we're asked to determine the position of the nodes and antinodes for the third harmonic, as well as the vibration frequency for this harmonic. So we can start by summarizing the information we're given. We're given that the mass is equal to 40 grams, the tension in our string is equal to 49 newtons, and the length of our string is 8 meters. And we're asked to solve for the frequency of the string as well as the position of the nodes and antinodes. So first, we need to determine the wavelength of our string. And we know from our equation that our wavelength is equal to 2 times the length of our string divided by the number of our harmonics. And since we know the length of our string is 8 meters, and we're given the string is in its third harmonic, we can solve for the wavelength of our string. So 2 times 8 meters divided by 3 for our harmonic will give us a wavelength that is equal to 5.33 meters. And now that we know our wavelength, now we can solve for the position of our nodes and our antinodes. So we reserve nodes at the end of each string, as well as at the end of each standing loop. And so we see between our first node and our third node, our second node is halfway between our wavelength. Therefore, our second node is our half our wavelength, and that our fourth node is 3 times our wavelength divided by 2. And then our first node is at the beginning of our string. So our first node has a position of 0 meters. Our second node is half our wavelength, which is 5.33. So half the value of 5.33 is a value of 2.67 meters. You see that our third node is 1 wavelength, so it's a position at 5.33 meters. And that our fourth node is the complete length of our stretched string, which is given to us as 8 meters. So our fourth node must be 8 meters. So midway between each node, we have an antinode. So we see we have a total of 3 antinodes, and that halfway between our starting point to half of a wavelength is 1/4 of a wavelength, and that halfway between a half of wavelength to a complete wavelength is 3/4 of a wavelength, and halfway between one complete wavelength and 3/2 of a wavelength, 5/4 of a wavelength. So our first antinode can be taken by taking our wavelength divided by 4, which will give us a position of 1.33 meters, and that our second antinode, which is 3/4 of the length of our wavelength, will give us a position of 4.0 meters, while our third and last antinode is 5/4 of a wavelength, which will give us a value of 6.67 meters. Now in part B, we're asked to solve for the vibration frequency while it's in its third harmonic. Well, we know that frequency can be calculated by taking the wave speed divided by our wavelength. And we know the wavelength of our wave. However, our wave speed is unknown. Our wave speed is also equivalent to the square root of our tension divided by mu. Our tension is given to us, however, mu isn't. But we know that mu is just our mass of our string per unit of length. And we know that the mass of our string is 40 grams, which we have to convert into kilograms, which is a value of 0.04 kilograms divided by 8 meters, which will give us a value for mu to be equal to 5.0 times 10 to the negative third kilograms per meter. Now that we know mu and we know our tension, we can solve for the velocity of our wave. So 49 divided by 5.0 times 10 to the negative third, taken to the square root, will give us a wave speed that is equivalent to 99.0 meters per second. Now we know our wave speed, we can calculate it into our first equation, where our wave speed divided by our wavelength will give us our frequency. So if we plug in our values, given that our velocity is equal to 99 meters per second divided by a wavelength of 5.33 meters, will give us a frequency that is equal to 18.6 hertz.